Hi. So this is going to be a continuation of the homework. This is on chapter 4. So again, we're going to continue writing electronic configurations for ions here. We're going to continue writing condensed electronic configurations. I'll ask you to do a couple of full ones on the test maybe, but full ones are for, like, babies of chemistry. We're professionals here. We write only condensed formulas. I'm just gonna ask you to write full because it's a requirement in the curriculum, and you gotta know how to do it, and I gotta prove that you know how to do it, etc., etc. But hopefully, we're good with writing condensed formulas. We just put the noble gas. Okay, that took a lot of erasing. Okay, lithium plus. So it has lost a electron, and so we have helium configuration. So I mean, writing the full form of that is nice and easy. So why not? But as you can see, these ions, especially the calcium stable ones, just go back to noble gas configuration. This will be argon. Bromine minus, it's gained electron, so it has krypton configuration. O2 minus has gained 2 electrons, so it has neon configuration. Draw Lewis structures for the chemical species. No Lewis structures for ions will be asked. We're not doing this either because those were grade. Okay, go away. That's grade 11. So we know MgX, to which main group? X has to be group 16 because that's a 2 minus and magnesium is 2 plus. So when both of them cancel out, they have no subscripts. SO4 is a 2 minus ion. So if it was X2, that means there's nothing around the SO4. That means there's a group 1. So that's just group 1. X2O3. So that means the 2 has come from the O2 minus. So it was something like this. X3 plus O2 minus forming the ion. And so this was a group 15 element. The group 15. 15? Am I getting that wrong? Yeah. I am. I think that I'm getting this one. This group 13 forms 3 plus positively charged ions. Group 15 forms negatively charged ions with 3, and those aren't the ones we're looking for. We're looking for positive ions with 3. CO3 is a 2 minus ion, so if we've crossed that over and there's no 2 that's missing over here, that means there was a 2 plus that has gone down over here and cancelled out. So therefore this is a 2 plus, so that means that's a group 2 from the periodic table. Properties of ionic solids, very, very important. We need to know some of those properties. Decreasing, okay, we're not going to do that. Electronegativity, I'm not going to ask you these questions. Hopefully, again, we look at our periodic electronegativity series, the periodic table that I gave you with all the electronegativity values. We just subtract and then we figure that out. Again, to determine whether it's polar or non-polar ionic, you just take central atom, you subtract this atom. All the questions that we have to do, obviously, this is important because this is like almost the first step before we get into VSEPR theory. We have to figure out, okay, first of all, is this covalent? In which case we continue with our Lewis diagram and our VSEPR as we've been practicing, or is it ionic? In which case our Lewis diagram just looks like, this. Is this our Lewis diagram that we're drawing? So this is a very important step, but hopefully we know how to do it, so I won't be asking you Lewis diagrams of ionic, and I won't be asking you to identify ionic versus covalent, but we do have to know that. So I think none of these questions are really interesting. Yeah, we didn't do much of trends, just because it's in the textbook, but it's not really in for the curriculum expectations. That was mostly grade 11. So we're sending you off to university in the hopes that you remember grade 11. And again, if this is not true, you always know I would highly recommend looking at your textbook, maybe doing some like reading Obviously not now, but in the summer before university starts, perhaps, just to get refreshed on some of the grade 11 stuff. University is going to be a flurry of things, and it's always good to be prepared. That being said, hopefully none of you are chronic procrastinators like I am, but you'll survive. It's more fun and less fun if you don't know anything when you go to university. That's it's kind of hard to explain, but I'm getting off topic here, so we're gonna jump right back into molecular shape and polarity. This has to do with so draw Lewis structures for each of the following molecules: ions, blah blah blah. Okay, so Lewis structures for each of the following molecules. NH3. So we're gonna draw. Let's do this. Where do you want it? Oh, we could do it at the side. Shouldn't take up too much space. We'll get quicker as time goes on. Actually, I think I can just draw it over here. Zoomed in. NH3. Okay, let's go. NH3 is 5 plus 3 equals 8 electrons. So N, H, H, H. 1, 2, 3, 4, 5, 6, 7, 8. Again, we'll practice using the VSEPR theory. You're obviously going to be looking at a chart, but I see that this is an AX3E, which means it's a trigonal pyramidal structure, and this will be polar. Again, hopefully, if you have a textbook, you're looking at you're opening your textbook to page 182, 183, 184. I can't remember which. But you're looking at your chart, your VSEPR chart, and noticing that this AX3E has a trigonal pyramidal structure. That will be polar because it has its lone pairs. This is good practice for what's going to be coming up, so we might as well get in the habit of doing it. CH4. 4 plus 4 is 8. I already know CH4 has 4 bonds, so that's going to be 8 things right there. This is going to be tetrahedral because it's AX4. All substituents are the same, no lone pairs. That's a nonpolar molecule. Again, that's not part of this question per se, but it's good to practice. CF4 is the same as before. It just has 4 plus 7 times 4 is 28, is 32 electrons. But all those electrons are essentially lone pairs around a fluorine and will not affect the carbon in any way. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. That's 32 electrons. This is also an AX4. This will also be nonpolar due to its shape. 5 plus 3 is 8. This is going to be pretty much the same as nitrogen. 1, 2, 3, 4, 5, 6, 7, 8 electrons I have drawn. This is again going to be trigonal pyramidal polar molecule because of the AX3E configuration around the central atom arsenic. BrO minus, there's just one bond here, Br and O. So the only thing to be determined is realistically where am I adding the lone pairs here. 7 plus 6 plus 1 is 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This will be stable. I will not make this a double bond due to the formal charge calculations, because now if you calculate formal charge, bromine has 0, oxygen has -1, which is okay. If I do the double bond, removing one of the ones on oxygen, because I can't remove one on bromine. Whoops. Undo. There's no undo. Sigh. My dots were really nice too. I can't believe. There we go. Nice dots again. If you undo this and make a double bond here, oxygen has more than 8, which is not allowed. So we cannot do that. We have to remove the double bond on oxygen. Remove a lone pair on oxygen and make a double bond, but that will give bromine -1 and oxygen 0, and the oxygen is more likely to take the -1 because it's more electronegative than bromine. So this would be a correct structure for this with the negative charge. H2S, 2 plus 6 is 8. There's only 2 bonds, so I know there's going to be some lone pairs around. 1, 2, 3, 4, 5, 6, 7, 8. This is a angular or bent structure with an AX2E2. This will be polar, just like water. H2O2. Let's try that one. That looks interesting. I'm fairly certain that this will look like this. We're not going to be drawing VSEPR shapes for complex molecules like this, but here we know we have two lone pairs. So the actual structure of this will kind of look like a bent around both molecules. So here we have O being bent, and then this O also being bent. This will be the shape of H2O2 that we might expect based on double VSEPR theory around two central atoms, but obviously we don't. The VSEPR theory was not part of this question. We don't have to draw VSEPR theory for these. Just get to interesting, fun stuff to draw. Here we can predict that nitrogen will be the central atom because it has the maximum number of bond forming capabilities. It can form bond to three things. Here we have a 7 plus 5 plus 6, 18. We have 1, 2, 3, 4. So I'm going to add 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Nitrogen does not have an octet. So that constitutes a problem. So I will probably try, let's hope yeah, that didn't work. I can't use my eraser if I zoom in this much. So I'm going to zoom back out because this is the last question realistically. And draw it nice and big over here. ClNO. This is what I started off with, but my nitrogen does not have 8. So I'm going to remove one oxygen lone pair and give this a double bond. So now nitrogen has 8. 1, 2, 3, 4, 5, 6, 7, 8. Oxygen has 8. Chlorine has 8. Everybody's happy. This is a neutral molecule. Let's calculate some formal charges. This is a 0. This would be a, nitrogen would be a 0 as well. Chlorine would be a 0. That's pretty much perfect. I mean, you don't really need to bother changing anything. This is good. So draw Lewis structures for each of the following ions. Consider resonance structures. We don't learn about resonance structures, so we're not going to consider it. Maybe I'll talk about it a bit on Monday just for fun. Just kidding. I don't want to scare you anymore. But it's good to know. It's good to know. Won't be tested, obviously. So we'll see how the day goes. CO3 2 minus. Let's try that one. Zoom in. Whoops. Okay, CO3, so carbon has 4. 18 plus 2 is 24 total, so I'm going to draw some right, so now I have 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Right now I know that my carbon does not have 8, so this is instantly incorrect. I'll have to erase one of these lone pairs, make a double bond so that carbon does have 8. And now basically I don't even have to check my Lewis diagrams, formal charges, because even if there is a +1, -1 discrepancy, my carbon can't take more than 8, so I basically stop here because I can't add any more double bonds, even if the formal charge told me to do so. So that's basically it. I see that even if I do check the formal charges, I get -1, -1, 0, 0, which is an overall charge of -2, and that's pretty much good. So we're going to move on. NO2 plus, that's 5 plus 6 minus 1. This is the first time I've seen that one. So this is a 10 electron total. So we have NO 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Nitrogen does not have 8. So we're going to erase the 2 here. Make a double bond right there. In this case, nitrogen still does not have 8. It only has 1, 2, 3, 4, 5, 6. So oxygen will have to get rid of 2 more and form a triple bond so that both of these things now have 8. Unfortunately, this leaves nitrogen with a formal charge of 0, oxygen with a formal charge of +1, which is not really ideal, but unfortunately, octet rule trumps the formal charge rule. I want both my nitrogen and oxygen to have 8, especially because they're part of the CNOF cannot overfill group, and therefore You cannot underfill either. Realistically, both of them need to have 8 before you even talk about formal charges. So formal charges, schmormal fraud. That came out wrong. You know what I mean to say. Formal. I guess it only works with the M. Okay, whatever. You don't care about formal charges because it's oxygen and nitrogen. You can't really change anything from an octet even if you wanted to, so formal charges basically do not matter. This one is more interesting because formal charges do matter in a chlorine because chlorine is not part of the CNOF. So here I have triple O. I have 7 plus 1, 8 plus 18 is 26, so 6. Plus another 6 is 12. Here I have 18. Here I have 24, 25, 26 total. So this will be a trigonal pyramidal VSEPR shape. But I do have to check for my formal charges here. I know I have -1, -1, -1, positive. I should write that down. -1, -1, -1, positive 2, which is not really the greatest of formal charges. And therefore I have to, on 2 oxygens, remove the lone pair at 2 double bonds so that my chlorine goes to 0, this oxygen goes to 0, this oxygen goes to 0. So now I have a -1 total negative charge. My chlorine does have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons, but that's okay for chlorine. So he's okay with that. So this is gonna be our structure for ClO3-. So chlorine will have 2 double bonds to 2 oxygens and a single bond to the other oxygen. And it has a lone pair of its own. So the shape here, VSEPR wise, does not change. It will still be an AX3E trigonal pyramidal, with a polar. Yeah, we don't really need that for now. Excuse me. So SO3- will look very, very similar to the chlorine, with the exception that there's only going to be one. We'll get to that. So 6, 18 is 24, 2, 26. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Again, sulfur has a +1. 3 oxygens have 3 -1s. That's not really great. My sulfur can take more than 8, so I'm going to remove a lone pair from oxygen, make a double bond. My sulfur gets 10 electrons, but that's okay. This will also be a trigonal pyramidal with an AX3E polar VSEPR shape, but it'll have 1 double bond and 2 single bonds. So now my formal charge is 0, 0, -1, -1. So that's okay. Dichlorofluoroethane has been draw a Lewis structure for this molecule. CH3CFCl2. CH3CFCl2. So I'm guessing it looks like this. These are both carbon atoms with tetrahedral geometry. We can add the lone pair, sure. Carbon's nice in the fact that it forms pretty straightforward bonds. You don't really have to. You could calculate all the electrons and put them around, but this is basically what the carbon compound is going to look like. Again, I'm not going to really ask you that kind of question. But N2H4. Let's see. Here, let's do some calculations. So 5 plus 5 is 10, plus 4 is 14. So that's the total. 1, 2. Let's assume each nitrogen. Let's favor symmetry for lack of a better word. For lack of a better idea. We start off where it's symmetrical. We prefer those things to happen. But now we needed 14, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Does each nitrogen have 8? Yes, it does. What is the formal charges? Each 0, 0, 0, 0. So this is probably the perfect structure for N2H4. N2F2, it's even more complicated. N2F2, that's 7 times 2 is 14, 5 times 2 is 10, 24 electrons. So N, N, F, F. Note that the shape will kind of be double. So each central atom, both the nitrogens are technically quote-unquote central atoms. So this will be a trigonal pyramidal geometry for both of them. So it kind of looks weird, but yeah. Here we have, sorry, how many electrons was this? 14, 24, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Ah, interesting. 23, 24? Yeah, but that doesn't really work because this nitrogen doesn't have 8, so I'm going to put that in a lone pair. Now everybody's good. Both nitrogens have 8, both fluorines have 8, and that's good. So this will be, again, a linear... No, it'll be an angular, double angular one. So similar to our hydrogen peroxide idea. Okay. So indicative coordinate covalent bonding. We didn't talk about coordinate covalent bonding, so we're not worried about that. SF6. Okay. That's a fairly easy octahedral structure. Just fluorine with... I'm not even going to count my electrons. This is what it looks like. That's basically it. BRF5. Let's see. 7 plus 7 times 5 is 42. This is going to be a trigonal bipyramidal structure. You can put in the electrons. 1, 2, 3, 4, 5, 6. But in this case, I do think that I'm missing a couple of electrons. So this one, you actually have to maybe count. 42, so 2, 4, 6, 8, 10. 10 plus 6 is 16, 22, 28, 34. 34 plus 6 is 40, so I do need 41, 42. So this is actually this is an AX5E structure, and we know that that would be a square pyramidal from our VSEPR chart. It will be polar as well. This is SF6 will be a non-polar molecule because it's one of the ones with 0 lone pairs with all same substituents. So that's that. This will be a square pyramidal structure. So that's the little structure for that. It will have a lone pair on the bromine. Very important to count here. Be careful. XEF4. This is basically square planar, you can tell, but 8 plus 28 is 36, so XE. Uh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 26, 27, 28, 29, 30, 31, 32. How many did I need again? 36, 34, 35, 36. 33, 34, 35, 36. So that is a square planar AX4E2 geometry. So if you look at your VSEPR chart, there's central atom, 4 bonds, 2 lone pairs. So that's AX4E2. PF5. Interesting. How would I do this? PF5. So I do 5 plus 35 is 40. So 1, 2, this is 10 plus 30 is 5 times 6 is 40, and that's a trigonal bipyramidal. Let's compare PI3 and CLI3. Let's see if there's space anywhere else. I guess not. Yeah, see, VSEPR 3 was from Mac University. Fun, right? Very close by. Okay, PI3, CLI3. I'm losing track of what I was doing. Oh, zoom in and do it here. PI3 is 5 plus 3 times 7 is 21, 26. So 1... so that's 6. plus 18 is 24, 25, 26. So this would be a trigonal pyramidal structure, AX3E, but CLI3 has 2 more, so that would be possibly 2 double bonds around the chlorine. So this is AX3E2, which will actually be a T-shape from our trigonal bipyramidal origin. But again, hopefully, again, we're used to doing this by now. Again, when you get enough practice, you can look at this and tell where or what shape it will be and how it looks. But again, practice is key. Count the number of electrons, throw them on until you get the structure. IF4 minus, so this one's interesting, 7, so this is 35 plus 136. Here we have 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, square planar AX4E2. And that will be a minus charge from the iodine, because iodine has a formal charge of 7 minus 4 minus 4 negative 1. So that's where it's coming from. That's fine, though. You don't really have to know that. It's just where it's coming from. Now we have the VSEPR stuff. Use VSEPR theory to predict molecular shape. Then we have polarity. Then we have review. Let me just see how much more we have to do. I don't even know what all this stuff is. Interesting. Oh, and then it's just that. So how about we do the rest of the stuff on another video, and then the only thing left will be the homework. I think we're on VSEPR. We were here. We were over here, so we will. It's a long video. We'll finish up, and then we'll do the remaining later. All right. Peace.